Today we're not just drawing a tank, we're building a working system. I'll model a water tank and plant 3D from scratch, add the correct nozzles, and explain the engineering reasoning behind each one. Why is it here? What is its function? What happens if it's missing? Then we'll connect a pump and insert a real valve model to turn this into a realistic setup you might see in an actual project. Let's get started. I've already created a vertical tank with a diameter of 2.5 meters and a height of 5 m, using plain ends. This type of tank is based on a real project I worked on. The actual vessel dimensions were slightly different, but I kept the overall structure and design concept the same. The first nozzle is a manhole. I selected standard dimensions for it. A manhole is essential for internal access to the tank. It allows inspection, cleaning, and maintenance, especially if the tank is used for water storage, where hygiene and periodic checks are important. In most cases, the manhole is positioned at an accessible height and oriented for safe entry, depending on whether internal access is required during shutdown or maintenance periods. The second nozzle is the vent nozzle. Since this is an atmospheric tank, we must allow air to move freely in and out. When the tank is being filled, the air inside needs to escape. When the tank is being emptied, air must enter to replace the liquid volume. Without proper venting, vacuum or overpressure could form inside the tank, which may damage the shell or roof structure. That's why even for a simple atmospheric water tank, a vent nozzle is essential for safe and reliable operation. The third nozzle is for the temperature sensor. In this case, I selected a DN25 nozzle with a flange connection. This gives a more rigid and secure installation, especially if we are using a thermal well or a larger temperature transmitter assembly. Very often in practice, DN15 threaded connections, usually female type, are used for smaller temperature sensors. The final choice really depends on the type of measurement instrument you plan to install. If the instrument is compact and lightweight, a threaded connection is usually sufficient. But if you expect higher mechanical loads, vibration, or need easier maintenance and replacement, a flange DN25 connection is a safer and more flexible solution. The fourth nozzle is for recirculation. If the water inside the tank needs to be heated, simple heating is usually not enough. To maintain uniform temperature throughout the tank, we install a recirculation line connected to a pump. The pump draws water from the tank and sends it back through a heating system, for example, a heat exchanger or heating coil, and then returns it to the tank. This prevents temperature stratification and ensures even heating. The fifth nozzle is for the level measurement instrument. Without a level sensor, we wouldn't know when the tank is full or when it needs to be refilled. Manual monitoring is unreliable, especially in automated systems. By installing a level sensor, we can control the filling process automatically. For example, an automatic valve on the water supply line can open when the level drops below a set point and close once the maximum level is reached. This not only prevents overfilling and dry running, but also optimizes the entire filling process, making the system safer and more efficient. The sixth nozzle is for the electrical heating coil. Here, I selected a DN250PM16 nozzle. The larger diameter allows proper installation of the heating element and provides enough space for mounting and sealing. When designing this connection, the tank diameter must be considered in relation to the coil length. The heating element has to fit properly inside the tank without interfering with internal clearances or other components. So the nozzle size and tank dimensions are not random. They must be selected based on the heating coil geometry and installation requirements. The seventh nozzle is for drainage. I positioned it 200 millimeters above the bottom of the tank. This elevation is intentional because the tank bottom includes a thicker stiffening ring and reinforced edge. Placing the nozzle slightly above the very bottom avoids interference with the structural reinforcement and simplifies fabrication. It also reduces welding complications in the most mechanically stressed area of the tank. The eighth nozzle is for emptying the tank. This connection goes to the pump suction line. I positioned it slightly higher than the drainage nozzle to prevent debris or settled particles from being drawn directly into the pump. By lifting the suction point above the very bottom, We reduce the risk of solids entering the pump, which helps protect it from clogging or damage. In practice, this small elevation can significantly improve pump reliability and reduce maintenance issues. The ninth nozzle is for water filling. This connection is linked to the supply line. On this line, we typically install both manual and automated valves, as well as a check valve. The manual valve allows isolation for maintenance, while the automated valve controls the filling process based on the level sensor signal. The check valve prevents backflow, protecting the supply system from contamination or reverse flow. With this setup, the tank filling becomes controlled, safe, and fully integrated into the overall system. The 10th nozzle is also for a temperature sensor, but this one is directly associated with the heating coil. Its purpose is to monitor the water temperature and control the heating process. When the temperature drops below the set point, the heating coil automatically turns on. Once the required temperature is reached, the coil switches off. This creates a controlled heating cycle and prevents overheating, improving both energy efficiency and system reliability. By placing the sensor close to the heating zone, we ensure accurate temperature feedback and stable operation of the entire system. I selected plain ends for this tank design. Since this is an atmospheric water tank, there is no significant internal pressure. Plain ends are structurally sufficient for this type of application and are more economical compared to dished or elliptical heads. They are also easier to fabricate and weld, which reduces manufacturing complexity and overall cost. In addition, because the tank is vertically oriented and supported properly, the flat ends provide enough rigidity for this operating condition. If this were a pressurized vessel, we would definitely need dished or elliptical heads to handle internal pressure more efficiently. But for an atmospheric tank, plain ends are a practical and cost-effective solution. Now that our model is complete, let's take a look at how these components actually look in real life. First, let's check what kind of oval manhole we can buy on the market. Oval manholes are commonly used for tanks because they provide sufficient access while maintaining structural strength. Second, let's take a look at how the heating coil looks in real life. For me, it actually resembles the type of heating element you might see in an electric kettle or even a coffee cup heater, just on a much larger industrial scale. In reality, these heating coils are designed for immersion inside the tank. They are built to withstand continuous contact with the water and are selected based on required power, voltage, and heating capacity. So while the principle is simple, converting electricity into heat, the industrial version is much more robust and engineered for long-term operation. Now let's take a look at what a temperature sensor looks like in real life. A flange connection is more robust. It provides better mechanical stability and is often used when the sensor includes a thermal well or when higher reliability and easier maintenance are required. Now let's get back to our drainage nozzle. Here you can see the internal drainage bend inside the tank. Instead of using a simple straight nozzle through the shell, I added an internal elbow that drops down closer to the tank bottom. The inlet point sits approximately 50 millimeters above the bottom plate. This design allows us to drain the tank more effectively while still avoiding direct welding in the stiffening ring area. It helps reduce dead volume inside the tank and improves overall emptying efficiency. So even though from the outside it looks like a normal nozzle, internally it is designed to optimize drainage performance. Since our vessel is atmospheric, I selected PN10 pressure class for almost all nozzles. For this type of tank, higher pressure ratings are simply not required. However, I kept one nozzle, the heating coil connection, as PN16. This depends on the heating coil manufacturer's requirements. Some suppliers provide flanges rated PN16, so we must match the specification accordingly. Now let's quickly add a vertical pump to demonstrate how the recirculation line is connected. The pump will draw water from the tank through the suction nozzle and send it back through the heating loop, creating continuous circulation. This helps maintain uniform temperature inside the vessel. By placing the pump here, we can clearly visualize the flow direction and understand how the recirculation system operates as a complete unit. This way, the model becomes not just a tank with nozzles, but a working system. Now I'm adjusting the pump nozzles to DN50 with PN16 pressure class. In many cases, standard vertical pumps are rated PN16 and are supplied with smaller flanges compared to the main pipeline. That's why we often need to adapt the line size to match the pump connections. The suction and discharge nozzles on pumps are typically smaller than the process line, so reducers are commonly used. The important part is to match the flange rating and size correctly to avoid spec mismatches and installation issues. Always check the pump data sheet before modeling, especially flange size and pressure class, to ensure your piping design matches the actual equipment. One important note about pressure classes: in smaller diameters, PN10 and PN16 flanges can sometimes have identical dimensions, the same bolt circle, and the same number of bolts. In those cases, they may physically fit together. However, in larger diameters, PN10 and PN16 flanges often differ in bolt number, bolt size, and drilling pattern. Because of that, they are not interchangeable. So even if the nominal diameter is the same, mismatched pressure classes can prevent you from connecting the flanges. That's why it's critical to check flange standards and pressure ratings carefully, both in real projects and in Plant 3D, to avoid connection issues and modeling errors. And here I created a simplified recirculation line, without adding all the detailed piping components, just to demonstrate the concept. The idea is to clearly show the flow path. Water is drawn from the tank, passes through the pump and heating system, and returns back to maintain circulation. This open end represents the outlet where the hot water would be used in the process. In a real project, this point would be connected to consumers, for example, a heat exchanger, process equipment, or a distribution center. While creating the vent pipe, it's important to talk about water expansion during heating. Water expands significantly when the temperature increases. For example, if we heat water from 20 degrees Celsius to 70 degrees Celsius, the volume increase can be noticeable. In a tank with a 2-meter diameter, this temperature rise can cause the water level to increase by approximately 8 to 10 centimeters. If you completely fill the tank without leaving expansion space, during heating the water level can rise above the maximum point, and you may literally get a fountain effect through the vent. That's why proper venting and leaving expansion volume inside the tank are very important in heated atmospheric systems. Let's change the level sensor connection from flange to threaded. Sometimes, in the model, I simply select a plain nozzle and then specify threaded instrument directly in the bill of materials. From a modeling perspective, this is often enough, especially at concept or preliminary design stage. The important part is to communicate clearly what type of connection is required. However, in detailed design, it's always better to match the nozzle type precisely in the specification. That way, the isometrics in BOM are fully consistent with the actual installation requirements. So it depends on the project stage. Concept modeling can be simplified, but final documentation should always be accurate. Now I'll show two types of valves that we can use in Plant 3D. The first type is a generic or visual valve. This is useful when you don't have the exact manufacturer data, and you just need a representative component in your model. It shows the function and location, but the dimensions are standard or approximate. Let's change the valve connection type to threaded or plain ones. For drainage lines, threaded valves are very commonly used. These lines are usually smaller in diameter and operate at low pressure, so a threaded connection is fully sufficient. Threaded valves are compact, cost-effective, and easy to install, especially for maintenance or temporary isolation of drains. Flange valves are typically used on larger diameters or higher pressure systems, but for simple drainage service, threaded connections are often the more practical choice. As you can see, when we select threaded ends, Plant 3D shows this box-style connection, which visually indicates that the valve has a threaded interface. This makes it easy to distinguish threaded components from flanged ones directly in the model. However, in some cases, especially during early-stage modeling, I simply use a plain end and then specify in the project specification or bill of materials that the valve is threaded. The second type is a real valve model with actual manufacturer dimensions. Since I don't have the real manufacturer model yet, I downloaded this valve from GrabCD. This is a threaded ball valve originally designed for DN40 pipe size. I scaled it slightly so it visually fits better with our DN50 pipeline in the model. Of course, this is only for visualization purposes. In a real project, you should always use the exact manufacturer model that matches your pipe diameter and connection type. That ensures correct face-to-face dimensions, proper flange alignment, and accurate installation space. If you have access to the real supplier model, it's always better to use it instead of scaling a generic one. Now let's convert this 3D valve into a live plant 3D valve with threaded ends. At the moment, it's just a static 3D model. It looks correct visually, but we can't properly connect piping to it. So I selected the AutoCAD block-based part creation option. Next, I specify the connection ports and define the directions in which the pipes should be routed. This step is very important because the port orientation determines how the pipeline will connect and how routing will behave. The next step is to select the option, Choose Block from Model. When I do this, AutoCAD recognizes the inserted 3D model and converts it into a block that can be used for part creation. As we noticed before, when we select threaded ends, Plant 3D shows these small cube-style indicators that define the threaded connection. Now let's try switching to plain ends, which represent welding connections. With plain ends, the connection is treated as a butt weld type. There are no thread indicators because the pipe will be welded directly to the valve body. This type of connection is commonly used in larger diameters or in systems where a stronger, permanent joint is required. So by changing the port type, we are not just modifying the visual appearance, we are defining how this component will actually connect to the piping system. And that's it for today's model. We started with a simple atmospheric water tank, defined all functional nozzles with real engineering logic, selected proper pressure classes, discussed expansion during heating, added a pump, built a recirculation line, and even converted a downloaded 3D valve into a fully functional plant 3D component. This is how a model becomes more than geometry. It becomes a working system. If you found this useful, subscribe for more practical plant 3D modeling sessions based on real project experience. See you in the next one.